So this session is titled as Generative Models for Inverse Imaging. And we have 3 talks scheduled in this session. And the first 2 talks are the papers accepted to ICCP. And the last talk, we're going to be the invited talk from Todd Ziegler. And without further ado, let me introduce our first talk. And this is a paper talk, and it's going to be delivered by Xiang. And I'll not read the title, and because he has his own first starting slide. So yeah, the floor is yours.
So my name is Xiang, and I'm from University of Michigan. Today, I'm talking about this work called decoupled data consistency with diffusion purification for image restoration. And it's a joint work with my co-authors from Michigan State University. And the department is computational mathematics and software engineering, something like that. Oh, sorry. Okay, so let's start it. So the topic of this presentation is about solving the inverse problems. So inverse problems, the goal is to recover some signal X from its noisy measurement Y. And the measurement is obtained through this forward operator, A, which can be both linear or nonlinear. And typically, the number of measurements are smaller compared to the dimension of your data. That means the problem is ill-posed. There are infinitely many solutions to this problem. That's why typically we need some prior for solving this ill-posed problem. And with deep networks, it has been shown that we can get good reconstruction from the measurement with very few number of measurements. So today's talk is about how to use diffusion model as one of the deep priors. So what is diffusion model? Diffusion model is a type of generative model that generates images by reversing a forward process. So the forward process basically is the process that gradually adds noise to the clean data distribution so that in the end, the data distribution will be close to isotropic Gaussian. So if you are able to reverse it, you can generate images from some samples from Gaussian distribution. To perform this reverse process, you need access to the score function. And in practice, people usually use deep networks to approximate this score function. And it can be learned by just doing denoising. So that is the basic of diffusion model. So let's go back to our question. So how do we use diffusion model to solve this inverse problem? So you see that here we are trying to recover X from the measurement Y. So this is a conditional generation problem. So ideally, we want some conditional diffusion model. So we'd like to have this conditional score function, which is the score function of xt given y. So there are many ways to get this conditional score function. You can do this in a supervised manner. That means you collect many pairs of x and y, and you can somehow inject your deep network with this measurement as some kind of condition. So you can train a conditional diffusion model to do this conditional sampling. But that will be very expensive because for every type of inverse problem, you have to collect data and you train this diffusion model from scratch in a supervised manner. So what people are trying to do is that we are not trying to train a diffusion model for every type of inverse problem. We want to use a pre-trained unconditional diffusion model to solve this inverse problem. So you see that we can actually decompose this conditional score using Bayes' rule. So it can be decomposed into those 2 terms. The first is just the unconditional score function. That is what we already have. But what is missing is this. This is called the likelihood gradient because it basically is the score function. It's a likelihood of y, the measurement, given some noisy sample xt. So as long as we can have this, we can approximate the conditional score, and we can do the conditional sampling to solve inverse problem. But the issue is that it's hard to compute this likelihood gradient. Why is that? It's because to get this, so we can look at this graph. It's taken from a paper called DPS. So the P y given x0 is easy. It depends on your forward process, and we typically have some closed form expression for this. We also have the closed form expression for the pxt given x0, which will just be some Gaussian distribution. But what we don't have is the px0 given xt. This is a very hard problem, and in general, we cannot compute this in closed form. So what people do, this is a very popular approach called diffusion posterior sampling. What it does is, instead of computing this exactly, it uses some approximation. So it just replaces this gradient term with the following likelihood. The simple likelihood is the measurement given the clean data sample. And they are basically getting this clean sample using this so-called Twedis formula. It's just the output of your diffusion model. Because diffusion model, basically when you do denoising, it gives you it tells you what is the average of all the clean images given xt. So this is some kind of mean image. And they just replace this x0 hat into this py given x0 to calculate this gradient. And we can write it out like this. And you can compute this in practice. So this is a framework. So at every time step, you are like pushing this xt, pushing your current sample along two directions. The first direction is the horizontal one. It's the unconditional score direction. And the second direction is the direction from the likelihood computation. And it works fine. It works very good. But there are some limitations, because you see that at each time step, you are enforcing this data consistency. You are trying to encourage your sample to be close to the measurement at every time step. That means you have to, if you really want your final sample to be to satisfy the measurement condition, you have to run this for many steps. But the diffusion model have advanced have big progress. So nowadays, you can just generate good samples using maybe 20 to 50 steps. That means, but for our particular problem, if you are using fewer steps, you cannot guarantee the data consistency. So you see that when you use fewer steps for solving this inverse problem, the final samples will not be close to the ground truth. And you may say that, what if I just increase the strength of this likelihood gradient direction so that we enforce this data consistency or measurement consistency more? But that will just destroy the structure of the diffusion model, and you cannot get very good reconstruction. Here is we increase the step size, but the algorithm just failed to generate reasonable images. And also, as I said, that it's hard to guarantee some consistency, and very often we observe that the generated images, they look kind of make sense, but if you look closer, something is not perfectly reconstructed. So the main issue is that you are trying to do two things at the same time. At each time step, you are trying to both go along the unconditional score direction and the likelihood direction. So you are doing two things at the same time, and those two things might be contradicting with each other. And the question is, what if we can decouple those two things? That comes to our proposed approach. So instead of trying to do data consistency and the diffusion sampling at every time step at the same time, we say that, what if we can alternating between enforcing the data consistency and then somehow applying the diffusion prior? So this is a picture I take from a textbook. So the idea is that we want to alternating between two processes. first process, we want to get closer to the sensor manifold, which is also the collection of data that satisfy the measurement condition. And after doing this, we try to use the prior and get some reasonable images, and we're repeating this process instead of trying to do both of them at the same time. So how to enforce data consistency? It's easy. We just solve this convex problem. Yeah. So VK here is some initialization you have. Maybe you can just initialize your optimization problem from some measurements, and you just run this using gradient descent, and you can get some initial reconstruction, xk. So as you can see, as I said before, the problem is ill-posed, so that there will be some artifacts in the reconstruct images from this step. You see the quality is very good. There are some strange artifact in it. And the next, how can we refine this low quality image using the diffusion model, using a pre-trained diffusion model? And what we propose is that we can first add certain amount of noise to this initial reconstruction. And after that, we run the diffusion reverse process from the noisy version of it. So here's some visualization of the process. So given this low quality image, we first add a certain amount of noise to start to it. And we just run the diffusion reverse process from this starting point so that we can get a refined image. And we want to provide some intuition why this works. So we may consider a very simple setting. That is, our distribution is basically a Gaussian distribution with mean mu and covariance sigma. And as I said before, what we do is we just add noise to this xk, which is the low quality image. We add noise to it. And it can be shown that because it's Gaussian distribution, we assuming the data is Gaussian, we can compute the diffusion model, the score functions in closed form. And with that, we can show that the generated images from this noise, adding noise, denoise process, we get something like this in closed form. So what this does is it's like you are doing something like a subspace projection. You have this image, you have this low quality image, and you are projecting it onto every eigenvector of the data covariance. And why this works? This works because images or other data, they are typically have some low rank structure in it. So you can imagine that the covariance is very low rank, and a lot of those low quality artifacts here, they will not lie in the subspace spanned by at least the top singular vectors of this covariance, so that doing something like this, you are basically getting rid of all those strange artifacts that are not lying on the dominant direction of your data. Yeah, so that's the intuition. We are doing some correction using the subspace projection, at least under this Gaussian setting. So that is the intuition of why this works. So here's the overall framework. We first do the data consistency optimization, and we do this purification, this correction process over and over again. And here's the process, what the process looks like. This is an impinging example. So for the data consistency, there's nothing you can do in this masked region. But with the purification, the correction process, you get something reasonable, and you repeat. After repeating this, you get a good reconstruction in the end. So here's some qualitative results. You see that the reconstruction quality will constantly improving. But on the other hand, if you just do the consistency, data consistency, you get a flat curve. And it's effective on many different inverse problems. And it can be implemented in a very efficient way using few-step diffusion models or diffusion samplers. Like you can even use that on consistency models, which is just a one-step diffusion model. This is result from the consistency model, and we get a better data consistency in the end. And that's all of my presentation. That's the message.
All right, I think we have time for 1 or 2 questions.
Yeah, please.
Thank you. I'm wondering, this process of adding noise, do you do it just once, or do you do it with multiple noise seeds and then do some kind of averaging?
So we do it for multiple times, right? It's an alternating process, and each time we are adding different noise to it, so it's random.
Right, but each time you add noise, you get multiple inferences, and what do you do with those multiple inferences? Do you average them? Do you mix them together somehow?
Sorry, so we add noise to it, right? And we run the reverse process, so we get a single image.
Right, but you only do that once.
Do that once.
With one noise realization.
Yes.
Okay, I'm suggesting maybe you could do it with multiple noise realizations, and whether that would be advantageous.
That might be.
Okay.
Thank you for the question.
Yeah, I think it's a really good idea to decoupling the data consistency and the denoising part. But I'm wondering that because like there are a lot of parameters, you mentioned that you need a properly chosen number of steps, and then you also need to have a decaying schedule for it to, like, during the iterating process, to let it converge. So I was wondering, like, for different inverse problems, do you feel like you need to adjust these parameters, and do you have like some guidelines for, if I want to apply it to a different inverse problem, do you have a guideline how to choose this, like the starting number of steps and how the decaying schedule should look like?
So in practice, we actually we don't have this parameter, but we do need to choose a decaying schedule. But what we do is we're just using a linear schedule. There are some papers, they have similar ideas, and they use more complicated ones. That is one thing you can try, like use more advanced scheduler, because diffusion model is shown that some time steps matters more. Maybe you should sample more from those region, those time steps region. And also, yeah, I agree. There are many hyperparameters, and I have to tune them carefully for each problem to get very good result. But I think for those type of alternating algorithms, the problem is that you have to choose the hyperparameters. But for the DPS, I feel like if you don't want to tune that much, you can use diffusion posterior sampling based algorithms. So this DPS, I feel like this type of method, they are more flexible because they don't have that much hyperparameters. So I will suggest algorithms like that if you don't want to fight the parameters. Yeah.
Thank you.
All right, due to the time limit, let's move to the next talk. Thank you. Again, thank you to the authors.
Thank you.
All right, the next talk, we have Ishan presenting this nice paper, Imaging 101. So due to the time limit, I think we're gonna have only one question for this paper after the presentation.
Thank you very much. I'm Yixuan Jia from the University of Michigan, and I'm presenting this joint work with our colleagues from Peking University, Beihang University, and the University of Chinese Academy of Science. This project is led by Professor He Sun at Peking University. And our paper is Imaging 101. It asks one simple question. Can today's LLM coding agents actually solve a computational imaging problem end-to-end? Just a very quick framing here. In computational imaging, we measure something that is indirect, noisy, and incomplete, and we recover the hidden signal from it. Y equals to A of X plus noise, where A is the physics of the instrument. And like black hole imaging, CT, MRI, seismic inversion, microscopy, they are all physically very different. But mathematically, they are all the same object, which is the inverse problem. And this object is the engine underneath a giant amount of modern quantitative science. So, but here is what it actually takes to solve one of the questions. So you pre-process the raw measurements into the quantity the algorithm expects, and then you implement the forward operator, and usually it's edge ones. You pick and run an inversion algorithm, and finally you visualize it. So these 4 couple stages make it a long horizon task. And that matters because long horizon is where agents are weakest. And a lot of expertise never appear in the paper, like unit conversions, normalizations, signs, and access conversions. They are all the things that you learn from the advisor or from 3 weeks of debugging, not from the methods chapter in the paper. And worst of all, the errors are silent. A wrong preprocessing step does not crash, it just propagates all the way down to the chain. And you will get an image finally, and that looks completely possible, though it is physically very wrong. So the question is not can a large language model write code, it is about can a frontier agent do this pipeline reliably? And today there are many benchmarks. Existing benchmarks treat the agent as an analysis. They hand it to a prepared artifact behind a clean interface. So the task is short horizon. The correctness is something you can see. However, computational imaging asks the agent to be the instrument. It starts at the raw measurements shaped by the physical operator. The pipeline is long horizon, and the correctness is something you will have to compute because the wrong physics still runs and still looks very plausible. So a benchmark for this has to be 4 things. The first one, paper grounded, and then execution graded, and then stage localizing, which is we need to tell where the agent breaks the pipeline, and finally, the extensibility. And that is our imaging 101. There are 57 tasks, 6 scientific domains, 3 evaluation tracks, 7 frontier LLM models, and it is built to meet exactly those 4 requirements. And let me spend the next 2 slides on the 2 design decisions that make this trustworthy, because that's really what a benchmark has to earn. And the central design principle is this. So we have like black hole imaging, low-dose CT, and many other modalities. They share not the same physics, but we canonicalize every one of the 57 tasks into a single template. That is the same 4 stages as 4 source files, the preprocessing, physics model, solvers, and visualizations, and always these 4. And that one decision is what biases everything else for the agent, for the grader, and for the community. So the standardization is what turns the 57 heterogeneous papers into one benchmark. So how does a task get built? There are actually 5 stages, and a human was monitoring all of them. First of all, reproduce. We build an isolated environment and debug the original code until it reproduces one exact figure or one exact number from the paper. So everything downstream is derived from that and verified run as a ground truth. And second, we canonicalize into the template we just talked about. And third, we calibrate the bar relative to the reference run. For example, the NCC should be at most 10% less, and the NRMSE should be at most 10% more. And fourth, we synthesize a unit test for every function with fixtures captured by instrumenting the reference run. And finally, we write a plan and executed tutorial notebook. So you can see our benchmark structure over here. We have the benchmark, we have the README, and we have the data, the source files, a plan, and evaluation harness, and also the notebook. Okay, and the benchmark has 3 evaluation tracks asking questions from 3 different dimensions. So first of all is the planning. We ask if it knows the right approach. So the agent writes an approach document and a design document. An LLM judge just tells the difference between it against the reference plan, and the 2 blinded domain experts must independently agree on each of the 3 components, including the preprocessing, physics, and the solver. And next, function level. We ask if the agent can implement each piece of the pipeline. So every function gets a unit test that checks numerical parity against a reference fixture with tolerance as high as 10 to the minus 10. So 10 reflections rounds are allowed to get it right. And finally, end-to-end, we ask if it can integrate a full working solver. It writes the entire pipeline, runs it, and we score the reconstruction against the thresholds up to 5 rounds. So the same task, same 4 stages with 3 different evaluation protocols, like knowing, implementing, and integrating. Okay, so let's take a look at the scoreboard. Planning goes first. So does it know what to do? And the good news is that naming the solver is relatively easy. Like 75 to 93% across the board, models know that this is a phase retrieval problem, something like that, or that you should reach a TV regularization solvers. But the bad news is about the preprocessing. It is the weakest dimension for every single model, around 68% on average. And that is exactly the implicit tacit step I flagged at the start. It isn't just stated in the problem description, or it just quietly gets skipped. And when you require all 3 dimensions to be right at the same time, the best model sits at 53%. That's only on planning alone, and before anyone has written a single line of code. And now we ask if it can implement. So this is the module granularity, which means that the module passes only if every function inside this module passes own unit test. And the preprocessing is now the easiest module because, and the inverse solver is the hardest, as low as 10% for the weakest model. And getting all 3 modules right simultaneously collapses to at most 23%. The strongest model here gets 13 out of 57 tasks fully correct at the module level. So by the way, note the inversion here. Preprocessing was the hardest thing to plan, but it's the easiest thing to code. So knowing and doing are very different failures. And now let's take a look at the same runs per function and the picture inverse. So most individual function passes 70 to 90%. A failure module is just 1 or 2 critical functions, typically the core forward operator or its adjoint that may sink the whole module. And when we classify why they fail, so numbers are not shown here, but the single biggest category, 42%, is numerical convention drift, which is a sign, a scale, an axis order, a missing normalization, and the code can run, the shape are right, and the round trip test passed, but the physics is wrong. So one example is in our backup slides, in the multi-coil MRI, every single model dropped the MVUE coil normalization, which is the minimum variance and bias estimator coil estimation. It is not occasionally. Cloud reproduced that exact error 47 times out of the 50 runs. So the model knows the convention, but it just won't invoke it. And for the end-to-end, we ask if it can integrate. So this is the number many people care about. The best sandboxes model at the time we were working on this project, which is the Cloud 4.6 Opus, reaches about 30%, and the weakest is at 7%. The 2 things to note here. First, the rounds to success stays very low, just about 2. And when the model gets there, it gets there very fast. So the reflection budget is not separating fast models from slow models, it's separating can from cannot. And second thing is that as a reference point, we also run a cloud code, which is a black box agent with a real shell and a package manager on the same 57 tasks. It reached about 56%. So the richer execution affordances clearly help a lot here, but it still fails on nearly half. And I want to be very clear about these numbers here. So every one of these tasks is published, solve the problem with the data handed to you, and the domain expert would be expected to get all these 57 correct. So now, 2 cases where errors survive, and because they tell you where these metrics can and cannot do. So let's first take a look at the black hole dynamical imaging task. We want to reconstruct the time-varying movie from a sparse interferometric measurements. The reference method star warps models frame-to-frame motion with a warp operator. And our README even hints at it, and Cloud just threw it away and modeled the dynamics as identity plus a white Gaussian noise. Essentially, it just says, just assume it is static. And it passed. The test sequence happens to move very slowly and smoothly, so the simplified prior still lands inside our margin, and visibly worse than the reference, but all above the threshold. So a physically weaker model can pass when the data does not stress the missing prior. Image quality metrics alone cannot certify the physics here. And here comes the mirror image. In the sparse view CT task, we have 30 views with TV regularization. 2 unit tests failed. the radon operator and uses the sticky images interpolation convention, and the back projection scaling didn't match the reference solver. But when end-to-end, it recovered. Why is it? Because those bugs were very loud. They were like shape mismatches, a huge NRMSE. The reflection loop gets a real signal, rebuilt both the forward model and the solver. And they finally converge to a self-consistent vista by round 5. So here, loud errors get fixed. Silent convention drift does not. And that is exactly why we keep all 3 tracks instead of reporting just a single number. Like the end-to-end score alone would just have told you the agent working on the CT task was fine, the black hole agent was fine, but it would have been wrong about both. So here comes the question, where's the path forward? From our perspectives, first, scale up. So more tasks, more modalities, and then retest. We want to see if the failure modes still hold at scale, or other artifacts of just this 57 particular tasks. And 7, this is the direction we are most excited about. We want to distill the skills. For each task, what is the minimal set of the domain skills you actually need to solve it? And then we can test them causally. Like we handle an agent, the skill on a task, it reliably fails, and see whether it flips. The skill that turn a failure into a success are exactly the skills our community want to write it down. And third, close the loop. So every evaluation run leaves a trajectory, and what the agent planned, what it coded, and like where the numbers diverged. And we want to mine those trajectories to build agents that write their own skills, keep the ones that verify and specialize themselves for imaging tasks. And finally, please consider to contribute. We welcome community task submissions to broaden the domain and modality coverage. And to summarize, first in Imaging 101, we have 57 paper-grounded, execution-verifiable computational imaging tasks and a standard that community can extend. And second, there are 2 layers of failure. On the top, there are some generic coding bugs that everyone knows. And below, there are also some imaging-specific domain knowledge. And the path forward is to stop hoping to stop hoping the model to memorize them, but start coding them with some verified skill libraries. And finally, we have domain-specialized imaging copilots on top of them. Yeah, and code data and task leaderboards can be available here. So just a very, very quick go through. So here is our website. It's going to be released very soon. You can explore all the tasks here, and in each task you can see the background, the problem description, final reconstruction, and about the data description. And there is an executable notebook. You can see all the steps about each task. And also you can see the model results here. Thank you.
All right, we're going to have only one quick question over there.
Okay, thank you. Great talk. I have a kind of a general question. So, how far do you think the agents are going to replace us? Basically, you know, this is kind of the key idea of this paper.
Sorry, I cannot hear very clearly. Can you repeat the question for me?
Oh, I think the question is how long time it is going to take for the agent to replace these kinds of stuff?
To
right?
replace basically computational imaging researchers.
Yeah. Basically, like inverse problem solvers and like the things that you did, like when the leaderboards like takes the high number and then the researchers.
Yeah, that's a very good question. So you can see at the time we were working on this project, we only have the Cloud 4.6 Opus, and now we have Fable 5, we have Opus 4.8, and the leaderboard is always changing. But it's fine. I think the key message we want to deliver is still there. So it's like the agents should learn the skills that are not right in the paper, the method part of the paper. It should learn the skills that we know by heart, like the normalization, the access, the conventions, something like that. So when we ask a model about, okay, write down the math or physics for me, then we can say, okay, it can write it. But when we ask it to implement it, we can see there are many problems. So there are actually some engineering details that the model have already missed. Yeah.
All right. Thank you for the great question and answer. Yeah. Now we're gonna move to the last talk before the lunchtime. So we're gonna have Todd Ziegler from Harvard University. And his research is focused on modeling the interaction between light and materials and developing systems to extract useful information from measurements of light. So it's quite general introduction. And of course, he has many things that he has won, but I'll skip it for the sake of the time. And the floor is yours.
All right. So the work that I'm going to talk about today is primarily done by two recent PhD graduates from our group, Nicole Hahn and Dean Hazzini, along with a few others, including Ko Nishino and my colleague Federico Capasso. So to state the obvious to this audience, there are sort of unavoidable ambiguities when we're trying to infer things like shape and materials that explain a given image. If you take this image, for example, it can be explained by like a teapot shape object that has a uniform mirror-like material that's reflecting the surrounding environment. Or it can be explained by the same teapot shape object that's sort of diffuse or matte and has kind of been carefully painted with a matte texture that matches the image. Or it can be explained by what it actually is in this case. It's something that's flat and it's been painted or projected to have texture onto it. And so, in the past, we've often tried to find the single best explanation of an image, say through Bayesian map estimation or gradient-based optimization. But this is dangerous kind of in a sensing system or a front-end perception system because given the ambiguities, it's doomed to fail quite badly sometimes. So fortunately, generative models can sort of free us from this risky paradigm where instead, we can pursue like a generative sensing or generative perception approach where we can learn to stochastically draw samples from the distribution of possibilities that explain a given image. And so what this talk is about is sort of how to design these generative models so that we can reliably produce really diverse samples that span the full set of explanations. And I'm going to do this kind of in three little vignettes that are sort of loosely related to each other, kind of think of them as three little short case studies. And the first one starts in this kind of simple like matte world where all the objects are known to be gray and diffuse. And given a single image, we just want to infer the 2.5D shape. And this is the classic shape from shading problem. And so here's an image in this matte world. Right, the varying surface orientations relative to the light sources lead to these shading effects that give us a really clear sense of surface shape. But this image is actually, I chose it because it's not a real image. It's actually a doctored photograph. It's a manipulated copy where someone's taken the sort of top hill and cropped it out and shifted it left-right. And what's interesting is that our perception of shape is almost completely unaffected by this manipulation, even though in the modified image, the sort of dramatic inconsistencies globally in the lighting. So that kind of gives us a first useful observation in this matte world, which is there seems to be some kind of computational shortcut that allows us to infer shape without inferring precise lighting. And the second observation is that, from previous work, we know that, there's some math to kind of back up this data this observation of being able to get shape without precise lighting. So if you just, consider a single point here, a single pixel in this image, and you take first and second derivatives of intensity there, and you choose any kind of dominant local light direction that you want, and you run these through the classic Lambertian shading equation, one can derive a set of polynomials that heavily constrain the set of local quadratic shapes at that point. And then, importantly, these constraints are completely independent of the assumed local light direction. Okay, and then the third and the final observation that we can draw upon is that we know, like I said, that there are these global perceptual and mathematical ambiguities, even in this really simple matte world that we're talking about, including convex-concave flips and GBR stretches and tilts that all mathematically explain the given image. So given all these observations, a few years ago, Nicole set out to design a generative model that could produce samples that cover these diverse sets of possibilities. And after trying several attempts, here's the design that she came up with. So what we did is we just collected a small data set of 3D objects and rendered them using various viewpoints and lighting configurations. So this is all synthetic training data. And then just extract little 16 by 16 patches. And we train a little tiny 10 megabyte conditional denoising diffusion model that, given a sample of image, generates samples of shape represented by these little surface normal fields. And that's all the training we do. There's no more learning after that. And then when we want to deploy this on a new image, we just apply it in patches at multiple scales. And during the denoising diffusion process, there's some guidance that goes back to sort of guide the per patch denoisers, so they all just don't do random things. They're sort of coordinated. And the loss that we use to kind of stitch these patches together just encourages them to have constant curvature at their seams at adjacent patches. So it's very, very simple MRF-like energy. And this model, you can see it's very bottom up, right? Almost all of the neural capacity is being devoted to doing things locally, and the only global thing tying it together is this kind of handcrafted pairwise smoothness prior. All right, and so despite its simplicity, right, what we find is that it works really, really well. So it generalizes from these kind of everyday objects, patches of everyday objects it was trained on, to these kind of, purposely built ambiguous images that are very different from the training set. And it gives us both the concave and convex explanations and various GBR stretches and tilts. And so for comparison, right, if you take prior models and apply it to this image, they all only produce the concave explanation. And interestingly, this is true even for these sort of very large stochastic generative models that are based on adapted stable diffusion. Right? They all collapse down to this single mode and fail to capture the diversity of possibilities for this image. And then we also find that this model generalizes really well, sort of crosses the sim to real kind of barrier without any extra fine tuning, generalizes well to photographs, even though it was trained totally synthetically, including these ambiguous ones where you see that it produces both convex and concave explanations. And if you're like me, you only see kind of the sort of concave explanation. But if I take this image and I rotate it around, it'll flip for you. So just watch while I rotate it, see if you can hold on to this concave explanation, and eventually it'll pop and go convex. All right, same goes for the other one. Okay, so all right, so the next example, we've sort of started in this little mat world, so now we kind of want to expand out to a more realistic situation where we're broadening our task. Now we need to infer the 2.5D shape and the materials of what we're looking at, again, from one view. So now there's this interplay between texture, reflectance, and shape that causes even more ambiguity. Right? And the way that we're going to handle this is we're going to exploit just a very small amount of motion. And this is kind of inspired by the instinct I have when I'm examining something very carefully to kind of move it around a little bit to better understand what's going on. It's also inspired by one of my favorite perceptual demonstrations. This one is the shinier matte demo from Daniel Kirsten's lab. So we know that this static image is ambiguous and can be explained by at least these two ways that I showed on the left. But as soon as it moves, the shiny explanation jumps out and the ambiguity goes away. And then if you switch and render it with diffuse motion, right, the percept immediately changes. And it's so strong that it overrides your sense of material permanence. Okay, and then there's also some math, to back up the utility of this small motion as a shape cue. So if you just consider the subset of explanations for this image here that correspond to a uniform mirror material, right? There's still ambiguity even if you lock down that material choice, because any change in explanatory shape can just be compensated by a change in the reflected lighting environment. But once there's motion, right, the observable optical flow field that you can see is actually independent of the lighting environment. And and there are local mathematical relationships that heavily constrain the surface curvature at a single image point. And you can do things, for example, like use this to recover the shape along an entire characteristic curve on the surface, just given a single initial condition. Okay, so inspired by all of this, we set out to make a diffusion model that takes a short video of object motion, just 3 frames. And what it does is it generates samples of the corresponding 3 frames of surface normals, diffuse albedo, and spatially varying parametric reflectance maps. And here's how the architecture looks. So you just, you concatenate these input frames here with your noise seeds, and then you recurrently process them into your output normals, albedo, and reflectance for the 3 time frames. And now we know from the first model that I showed you that this kind of multi-scale bottom-up processing really helps with diversity and generalization. So we created diffusion architecture here that only has global attention at a very coarse resolution. And at very fine resolutions, you have purely local shift invariant processing. And so we have sort of neighborhood spatial attention, mixers across the time frames, and mixers between shape and material within each frame. And then we train our model again from scratch, just with synthetic renderings, about 1,000 objects, moving at varying speeds, including 0 speed, which just corresponds to looking at a static image. And here's an example of the results of the model's output. This is synthetic here for a novel synthetic test image. So here's, I like this example because it's hard for me when I look at this to kind of pull apart what's lighting and what's texture. But then I have, no trouble doing that once it moves. And this is what the model sees when it generates its output. And as comparison, right, here's the output of another model. This is another video-based model called Diffusion Renderer, which is several times larger, and again, built upon stable diffusion, and you sort of see that it struggles to generalize to this situation. Here's a result where we take the same model. Again, there's no fine-tuning or anything, and apply it to captured photographs. So this is now captured images from 3 nearby object rotations. And the model, sort of crosses the sim to real gap again without any fine tuning, and it gives us, finer details here and better temporal stability than alternatives. And then here's one more result that I want to show you, kind of demonstrating the diversity of the model's output. Right, so here we give the model this image, and we just give it 3 copies of this photograph. So it's just seeing a static image. And like the first model I showed you, it generates sort of convex and concave explanations. This time it also predicts the spatially uniform albedo maps that would go along with these shape predictions to predict the image. But then in addition, right, it also generates a third kind of postcard explanation that says, it could be a completely flat shape, and this shading could actually just be painted on as texture. Okay. So far, the running theme here has been that it's helpful to put structure into these generative sensing or perception models, and I'll emphasize this just with one more example. This time, something maybe that's closer to this community, which is a computational imaging scenario. And so this is just the classic problem of trying to make a single-shot, visible range, hyperspectral imager, but we want to make one that's especially small and especially light. And so it just has a single diffractive optic, like a DOE or a meta lens, and then it has a grayscale filterless sensor. No Bayer filter or anything on this sensor. And then we pair this with a reconstruction algorithm that infers a 30-channel hyperspectral cube. And notably, the spatial resolution of the output cube is the same as the spatial resolution as the sensor. So there's no kind of extra pixels on our sensor. Okay, so now the idea, of course, is to use some kind of optic that mixes spectral information into the spatial dimensions of the sensor, hopefully allowing the reconstructor and its built-in prior to decode it. And as we did in the first 2 examples, I'll take a sort of a generative, a diffusion-based approach that produces stochastic samples of hyperspectral cubes that explain the measurement. And we want to do this like before. We want to train this thing from scratch using very modest amounts of training data. In this case, it's kind of out of necessity because there's just not that much training data available. So we follow a recipe very much like the first example I gave you, right? So first thing we do is we generate some synthetic training data by choosing a point spread function that we know that we can fabricate, simulating some measurements. So we take some captured hyperspectral cubes, we simulate what a measurement would be with that point spread function, and then we extract patches from this. And we train, you know, a 150 megabyte diffusion model that, conditioned on a measurement patch, reconstructs a hyperspectral patch. So now, in addition to the fact that I've seen this patch-based approach work for another problem, we do generation in patches here for two reasons. So number one, it helps circumvent the challenge of training data, because I can get a lot of patches from a single cube. And number two, again, we know from previous work that hyperspectral patches, right, have pretty substantial spatial spectral statistical structure inside of them that ought to be exploitable as a prior. Okay, so again, like, you know, training this patch model, that's all the learning we do. And then after it's trained, we deploy it to a new measurement, kind of in any size that we want, just by applying it in non-overlapping patches. We patchify that measurement. And then during the denoising process, we coordinate all of the samples that are being generated by these parallel patchwise denoisers using, again, like an inference time guidance that is feeding back based on a loss that says that if we take all of the intermediate noisy patches, assemble them back into a full frame noisy cube, then according, you know, they've got to convolve back by the PSF to the input measurement. And so that sort of coordinates all the patches and helps stitching at the seams. And so you'll notice, like in the first model in my talk, you know, this is very bottom up with all of the neural capacity invested in these little patches. And it's only the full frame PSF loss that's tying things together globally. And I'll let you, read the paper to sort of see how it outperforms kind of alternative reconstruction architectures and how we can deploy it to a real metal lens prototype with kind of minimal fine tuning. But the things that I wanted to highlight here are just two of them. So the first one is something that surprised me about this model, is that it can succeed even when the patch size, which I'm showing here in red, is fairly small relative to the blur kernel size, which is shown in green. And the reason why that surprised me is because, if you think about the forward process of what's happening at various wavelengths in this hyperspectral cube, the PSF is kind of throwing information outside of the measurement patch. And then at the same time, it's going to be throwing outside signal into the measurement patch. And so what that means is that's sort of forcing the patch reconstruction model to use its prior to overcome the missing and polluted signal. And then the final thing that I wanted to highlight is that, because we have sort of a model that produces diverse samples, we can use its variance of the samples to infer pixel-wise uncertainty, sort of the slow method of inferring uncertainty, according to Christina's characterization earlier on today. And so here's a simulation test for 6 different scenes. And we show our output models per pixel variance in the middle row here, and then on the bottom row is the actual error. And so this high correlation between variance and error sort of means that it can be a trustworthy uncertainty indicator, let's say, for scientific imaging scenario. Okay, so here's the take-home messages, right? The visual world's ambiguous. So visual sensing benefits from producing diverse hypotheses that then you can refine by action, let's say by touch or by moving around, capturing more measurements. Generative models make this possible. If you can put in kind of scalable, task-specific inductive biases, you can enhance generalization and data efficiency. And I think we can still draw on sort of classical vision and computational photography insights to help inspire more effective architectures. Thank you very much.
All right, let's have one question. Yeah, probably here. Sorry. Yeah, let's have 2 questions over there.
Yep. Thank you for the great talk. I enjoyed watching it. I have a question about inverse rendering, and I'm asking as a person who's been working on inverse rendering for the last 10 years. Back in 2016, 10 years ago, there were promises that inverse rendering techniques were providing. And one of them was to digitize everything in the world using images and videos, controlled environment, uncontrolled environment, and then re-render things using computer graphics and build a digital twin of the world. Some may call it metaverse or virtual reality, but that was one of the premises. In 2026, we have generative models that produce images and videos without any 3D priors. In this context, I wonder what promises or values that inverse rendering techniques can still provide.
So I guess is the question, like, do we need 3D? Is that your question? Like, do we need 3D models?
Yeah, I think we can frame it that way.
Yeah, so I think it really depends on the task, right? So I think a lot of the tasks that you described was sort of, geared towards human viewership, human experience, right? And I think, yeah, in that case, maybe we don't, right? Maybe we can just have generative models. But I think if you are wanting to build a system that's interacting with the physical world, right? So actually manipulating things and navigating around things, then I think, yes, we still need to be worrying about 3D. And then we also need to be worrying about actual physical accuracy, right? If we have systems that are making life and death decisions, then I think there's still a place for it.
All right, the last one, yeah.
Cool. Hey, super cool stuff. Really impressive. You can get at least a plausible or an idea of what the hyperspectral or multispectral image would be from a single monochrome sensor. If your goal were the more modest one of just getting RGB out of a monochrome sensor, does that vault this into the area where it could actually be like industrially interesting and practical to just start shooting our images that way?
So I think I'd ask Payman. So I don't know. I think that's a really good question. I imagine that, according to Payman's characterization, that maybe we could do that if we were willing to accept more hallucination. Like, I think and whether or not it's worth it, right? As you would gain a little bit in light efficiency, I suppose. Whether that is worth changing the whole industry versus just using smarter computational models and I think that's an interesting question. I've seen work, for example, in where you can use a metal lens above a grayscale sensor and use it to sort of direct photons as opposing to filter them out, right? And in theory, you get sort of a 20% efficiency gain or something like that in terms of light, but it's just not worth it to change the whole industry. We're really good at making these bare filter sensors. For this gain in light efficiency, it's probably not worth doing just for that application.
Thanks.
Yeah, fortunately, we have time for 2 more questions, actually. Yeah, there, right.
Thank you, great talk. So I'm wondering about, the capacity of these models to generalize to any like high energy peaks. My go-to example with any rendering engine or material system, whether it can render retroreflective materials the right way. And you showed an example actually in your knife of like a very good, there's a great illumination peak right there. Are you exposing an error here in the model, or can it actually do high energy or high frequency peaks?
That's a good question. I think in all of these examples that I showed, it's all kind of very empirical, right? We've just shown for these applications, we get better generalization if we use these kinds of structures. I haven't done any tests that I would sort of start to make general statements about what these can and can't do. But I do think it's really interesting. It was a real struggle to find diffusion architectures that don't just collapse down to a single mode and kind of make quick decisions based on kind of top-down recognition. And I still think there's a lot of room to improve it. Like we find, for example, this model is not as good at recovering all the concave and convex ambiguities of the first model that I showed you. So I still think there's a lot of work to do in figuring out how to design these things so that they train efficiently and generalize as well as they can.
All right, the last question. Over there.
Thank you. Yeah, I was wondering, like, for this specific model, like, how many generations did you have to make to get the diversity that you had? Is it pretty well calibrated, and is it calibrated, I guess, when you apply from synthetic to real data?
Yeah. So we literally just trained it on this synthetic data, and actually it was only trained on objects that rotate horizontally. And it generalizes, yeah, we find it generalizes to capture data like I showed you, and it even generalizes to, different kinds of motion. Like I think I have an example down here. I can find it.
When it comes to like the ambiguity, like if it's concave or convex, then for example, is like 50% of the outputs of the model, are they?
Yeah, no, that's a really good question. So this is a plot from the first model that I showed you. So you can take an image like this one, and you can draw, let's say, 50 samples, and then you can make a t-SNE plot of kind of where those are, and you can see this particular model generalizes roughly 50-50. So and this is the first model I showed you. If you take the second model and apply it to this data, it's not quite as good. And so it won't be balanced, and in some cases it'll just give you one or the other.
That's awesome. Thank you.
Wonderful. So let's thank our speaker once more.